All right, so last time we learned that the energy levels in an atom are quantized. And so with this information, we can take a look at the Bohr model of an atom. And this one's, it's a pretty simple model, but it's actually really good in terms of how much information it gives, even though it's quite simple. So in the Bohr model of the atom, basically the electrons travel in quantized orbits around the atom. So we have our nucleus in the middle, and then around it we have orbits, right? And so the electron is allowed to be on these orbits, but is not allowed to be in between these orbits. And so we can think about exciting an electron up to an orbit and then having it de-excite back down. So these orbits, we can give energy levels of n equals 1, n equals 2, and then n equals 3. And so since the nucleus and the electrons are attracted to each other, the further away the electron is from the nucleus, the more energy it has. So we can think about different transitions that it's allowed to have. So for example, if an electron went from n equals 2 to n equals 1, it would emit some light, and this would be a low energy transition because it's not falling far. If we think about something maybe going from n equals 3 to n equals 2, this would be a high energy transition. And you are allowed to do transitions in between. So you can have from like n equals 3 to n equals 2. And so this type of excitation would be something like red light, right? Low energy. And something like this would be something like violet light, high energy. So we can represent it in this kind of circular model. Another way we can think about it is in terms of energy here. And then these lines represent our kind of heights. So our energy levels are orbitals. So we can have n equals 1, n equals 2, and you can see the spacing here is quite large. And so one thing to note is that when we get to higher and higher n's, they get closer and closer together. So n equals 3 would be something like this. You can see the distance between 2 and 3 is smaller than 1 and 2, and then 3 and 4 would be even closer, right? So as we get to higher n's, we get closer and closer together. So let's take a look at this real quick. So we can think of in terms of energy here, right? N equals 1, n equals 2, n equals 3. And so we can have an electron here. We can have this electron absorb some energy. And then it'll excite to a higher orbital, right? But it can't be in between. It either goes to 2 or 3, or it doesn't. It can't go 1.5, it can't go 1 1/3, that kind of stuff. And so then it relaxes back down, and then it would release some light. So you can think of that in terms of that kind of light. This would be kind of a medium level of energy release between 1 and 2. Another situation would be, n equals 1, 2, 3. We could excite the electron all the way to the third energy level. And so when it de-excites, it's going to release high energy light, so something like purple light. And we can have other energy transitions in here as well. So n equals 1, n equals 2, n equals 3. So if we had an electron down here at 1, we could excite it up to 3. And then maybe it only de-excites down to, or relaxes down to 2. So this would be something like a very low energy light, something like red light. So the kind of cool thing here is if you have a 1 electron system, is that you can actually calculate the energy differences between these two. And so the equation is delta E equals this constant. We won't talk about this too much, but negative 2.18 times 10 to the 18 joules times 1 over n squared final minus 1 over n squared initial, right? And so let's take a look at an example of maybe something like this system, right? This third one. So what we're going from here is n equals 3 down to n equals 2. So let's calculate the energy difference or the energy the amount of light this would release, the energy of light that this would release. So delta E here, again, negative 2.18 times 10 to the 18 joules. That's just constant. And then if we think about our values here, our initial is 3. So that goes down here. And then our final is 2. So that goes right there. So it's 1 over 2 squared minus 1 over 3 squared. And then if you plug and chug that way through, you get a negative 3.03 times 10 to the negative 19 joules as your answer. The negative sign just means that you're releasing energy, right? Because we're going down in terms of orbitals. And then if we think back to Einstein, he said that energy is equal to hc over v. And so we can plug and chug these numbers in. So let's reorganize what we want to kind of solve here. Hc over lambda, my bad, lambda. Wavelength, what we want to solve here is for wavelength. What wavelength of light are we emitting here? So we can reorganize the equation to be hc over E. We calculated our E. This is Planck's constant, so it's 6.626 times 10 to the negative 34 joule seconds. And then this is the speed of light, so it's 3.00 times 10 to the 8 meters per second. And so we can plug and chug all of that stuff through, and what you get is 6.56 times 10 to the negative 7 meters, which is equal to 656 nanometers. And if you look at 656 nanometers, what you'll come up with is red light. And so we can predict right here that this one will indeed release some red light. So to us, this seems pretty basic, but back in the day, this was pretty groundbreaking that you could figure out these values to such precision using this quantized model of the atom. I think I have a picture somewhere. Yeah, this one. So you can just see, again, this picture just kind of shows the same thing. In this quantized view of the atom, our energy levels are quantized, and so they can only be certain values. So n can be 1, 2, 3, can't be 1.5, can't be 2.5, that kind of thing. And as n increases, our electron is in higher and higher energy orbitals.